Hello and welcome back. Unless you just stayed here because you fell asleep, in which case, welcome again. Android performance, we're going to talk about various things. We're done talking about memory. We wanted to talk about runtime performance issues. Some improvements in the platform recently, and some tips and tricks for getting better performance in your activities. If you weren't here before, we are still the same people. I am Chet Haase.
And Romain Guy.
And I work on the framework team on UI toolkits and animation and graphics and performance. And he used to.
Yeah, I don't anymore. So first, performance improvements. So Android 4.4 comes with a number of improvements that we've done on your behalf. So hopefully your applications will run better on Android 4.4.
You're welcome.
You're welcome. And the first one I want to talk about is called lazy measurement. So this one is a little special because it's only enabled if your target SDK version is 19 or higher. We tried to enable it for all versions of the platform, but some applications were relying on, I would say, undocumented behavior that should have been documented. Anyway, so change your target SDK version, it's going to make your app faster. So the idea of lazy measurement is that we're going to cache measure dimensions for all your views to avoid doing extra work when a view in your UI is requesting a layout. And we're going to keep that cache until per view until the next time that view calls request layout, at which point we're going to clear the cache. The idea is to greatly reduce the number of calls to onMeasure, and I'm going to show you an example of that in a few minutes. But first, let me explain what the problem was. So before Android 4.4, this is how measurement worked. So we have a view group and we have two children. When the view group needs to measure itself, it's going to first measure the first child, calling the measure method on that view. That child is going to call onMeasure on itself, and this is the method that you usually override if you want to do custom measurements. And finally, the child will send the measure dimensions back to the parent view group. So then the view group measures the second child calls onMeasure on itself, and sets the second set of measure dimensions. Now, if one of the children calls request layout, the view group has to remeasure all the children. But we had a very simple optimization. So here we'll remeasure the first child, we call measure, and we pass the same specs, so the same measure specs as the last time. And we have this cache of one entry where we remember the result of the last measurement. So we know the result of the last measurement. We know that we have not called request layout on that view, so that view has not changed. So we can return the cached value directly. We do not have to call onMeasure. So if that child is a view group, that means we do not have to go measure the children of that view group. And we can save a lot of time when measuring the window. The second child called request layout, so that child is marked dirty and has to call onMeasure again to redo the computations. So that optimization has been there since Android 1.0, and it was great. It worked really well. The problem is we have a couple of multipass layouts, in particular linear layout, when you use the layout weight attribute on the children, or relative layout, or any custom layout that you might have from a library that you're using, or a custom layout that you wrote. In a multipass layout, that optimization just doesn't work. So the view group measures the first child. We call onMeasure, we set the measure dimension, we do the same for the second child. Then the second child, I forgot, yeah, second measurement pass, so we have to remeasure the first child, calls onMeasure, set dimension, we do the same for the second child. Now the second child calls request layout, so we have to go remeasure the first child. But because we have a two-pass system, the cached value that we have does not match the last measurement pass. So even though that child has not changed, it has not called request layout, the framework was just too stupid to remember more than one value. So we have to call onMeasure again. And that was a cause of a lot of performance issues in very complex view hierarchies that were using relative layout and linear layouts. So now what we do is for multipass layouts, we remember more than one value. So if you have multipass layouts in your application, and if you're running on Android before 4.4, you should avoid using those multipass layouts, and we'll talk about that more in details at the end of this talk. Use fewer views. And starting with 4.4, you don't have much to do, actually. just make sure that your target SDK version is 19, so 4.4 or higher.
But use fewer views anyway.
Yes, use fewer views anyway. So with 4.4, what happens, so if we do our 2 measurement pass, so we do the first pass, then we do the second pass, then one of the children calls request layout. The child that hasn't changed remembers more than one value, so we're able to return that value directly, and we can save a lot of time. So this is an example. So I actually wrote a simple application. So this is the UI for the application. This is the view tree. And it's actually a very simple tree compared to apps out there. This is really, really that simple. And I tried to recreate the kind of tree that you see in a lot of applications. So we have a lot of linear layouts that use weights. We have a lot of relative layouts. But in the end, we only have 7 text views in the button, which is almost nothing compared to complex application out there. So now let's imagine that we call request layout on that button at the very top. So I ran that application on Android 4.3 and on Android 4.4, and I compared the performance. So on API level 18, it takes 6.5 milliseconds on the Nexus 4 or on the Nexus 5. On the Nexus 5, it takes 6 milliseconds to measure that tree. And it took 72 calls to on-measure to get the work done. With Target SDK version 19, we're down to 0.7 milliseconds, and we have only 14 measure counts. So all you have to do, again, just change your Target SDK version, and if you have a very complex view hierarchy with a lot of relative layouts and a lot of linear layouts with weights, you're automatically going to get that kind of benefits.
So there was a lot of work done in the last couple of releases on optimizing the way we use display lists. Display lists are an internal mechanism that we use. It's sort of an intermediate language that we use to batch up the drawing commands that we then send to OpenGL. So as you execute commands in Canvas, you call things like draw a line and draw a bitmap. As all of these things are executed, they are then in turn turned into these display list commands that go into these display list queues, and then eventually we send that information, we turn those into OpenGL commands and send it off to OpenGL. Prior to, let me see, when did merging and reordering hit?
4.3.
Okay, so prior to 4.3, we simply created the commands that would display your views. We have this hierarchy of display lists, and we would just execute that on every frame and send down all the information to GL. In 4.3, we did a lot of optimization work to look at what was actually in those and merge similar information and reorder it in a more optimal way to avoid thrashing OpenGL, to avoid changing state when we didn't need to, and process things in lower numbers of OpenGL calls in general. Basically, the more optimally we can use the GPU, the better performance you get in your application. State changes in particular are expensive for OpenGL because when you change the texture that you're using or the color that you're drawing with or the shader that you're drawing with, any of those changes can cause GL to sort of flush the pipe and move stuff around in order to get ready for the next operation. So the more we can batch things that are using similar state, the better performance we're going to get on the system in general. So here's an example. Here's a simple UI. You have a couple of buttons, a couple of checkboxes. Now, if we look at what this actually looked like, in the order of the drawing commands, so prior to 4.3, we would send down the bitmap that represents the checkbox, and then we would send down some text, and then we would send down another checkbox, and then some more text, and then a button background, and then some text, and then a button background, and some text. When we were able to actually reorder these things, it was a little more like this, which OpenGL is much happier with. We send down multiple operations that just draw the checkboxes and the bitmaps for the background of the buttons, and then the text. So fewer state changes, and then when we applied merging, we were actually able to issue fewer numbers of calls as well. Now these go down as one GL draw command that draws multiple bitmaps or multiple text operations from the texture. There was also...
So this is an example of what reordering and merging does for you in a typical application. So I took the contacts application and I just went to the contacts, the new contact screen. So you have a bunch of, there's text, there's a bunch of text fields, we have spinners, there's a couple of images. So without the reordering and merging, so that's before Android 4.3, this would take about 48 draw calls. So we would have to issue 48 different draw calls to the OpenGL drivers. And that's exactly what the app is actually doing. So we just have a one-to-one mapping between the number of draw calls in the app, so canvas to draw something, and the number of GL calls. With reordering and merging, we now have only 18 draw calls, which saves a lot of CPU time because there's not as much state change. And something to be aware of is that at the OpenGL level, what we use to actually do the rendering, every draw call comes with half a dozen or more state change commands. So we have to tell the GPU, okay, now I want you to use this program, and here's your matrix, and here's the set of triangles I want you to use. So the fewer draw calls we have, the fewer OpenGL driver commands we send, and there's a lot of overhead in those commands. So to give you an idea, so that same screen, without the reordering and merging, we are issuing almost 600 driver calls. And those are expensive because there's a lot of checking happening in the driver. And with the reordering and merging, we're down to only a couple hundred draw calls. So applications have got a lot more efficient. And in an application like Gmail, scrolling the list, like your inbox, for instance, this makes the scrolling about 15% or 17% faster on the Nexus 7. So this is a non-negligible performance improvement that you got for free. You have nothing to do in your application, it will just run faster. So another big change in Android 4.4 is something we call the Asset Atlas. So this is an example. This is not the final texture that we use, but this was a dump I took during development of the feature. So what we do is when we boot the device, we gather all the assets of the framework that we typically load in the Zygote process, and then we compute the best combination of those assets in a single texture for your device. So based on the characteristics of your GPU, based on the number of assets that we have, we're going to try to pack them all into a single image. The huge advantage of doing that is then we can create a texture for the GPU and share it with all the processes. So before the Asset Atlas, every application, every process would take a copy of a bitmap that was coming from the Zygote and then turn it into a GL texture. So every process, every app on your phone would have a copy on the GPU of the buttons or the text fields or the checkboxes. So now we have a single copy. So we're saving quite a bit of RAM. It's hundreds of Ks in every process. So when you have 20 or 30 processes running on a phone, we quickly save several megabytes of data. Another advantage of that is because everything is now treated as a single texture, the pipeline is able to merge a lot more drawing commands. So before, what Chet just showed you was, if we see that you're drawing the same bitmap twice, we can treat it as a single draw call, because it's the same texture. But now that all the bitmaps are in a single texture, we can do even more merging. So on the right side, you see how we actually draw the settings screen in Android 4.4 and the Nexus 7. And if you look at the very first frame, you're going to see the checkboxes being drawn. We have a checked box and unchecked boxes, and they're drawn at the same time as a single drawing command. That's because both the unchecked box and the checked box live in the same texture. And you can also see the text, for instance, being drawn in two separate calls. And this is completely different from the order of the views that you declare in your application. So it can make debugging a little harder for you if you use the GL tracer, because the ordering of the operations will be completely different from your layout. But this is very, very efficient. And there's more work. More work has been done around the Asset Atlas. So the merging we introduced in 4.3 also got a lot better in 4.4. So now we can merge 9 patches in better ways. If you're scaling bitmaps, we can now handle that, merge them with unscaled bitmaps, and so on.
So another optimization that took place at the display list level was, well, we have a lot of information down there. We've pre-processed all of the drawing commands. We know exactly what's going to go on the screen, so we can do some post-processing on that and say, okay, are there other things that we could optimize here, such as reordering and merging? We also take a look at whether there are any elements that are completely covered by other elements. That's a very strange description. It doesn't mean anything to me. What we're looking for is basically, do you have a background that is then covered by another background? That's the worst use case that we run into very commonly. It's really easy. In fact, it's trivial to create an application with an opaque background because you get that by default, right? So your window has a background that's going to be drawn every time the window is displayed. It's typical to also have a container, maybe a top-level container, that has a solid background color. That means that we're drawing the background of the window, and then we're drawing the background of your top-level container. And maybe there's some other containers along the way that are also drawing opaque backgrounds. And so you're making us draw, you're making the GPU draw twice the entire size of the screen just because there's two backgrounds covering the exact same pixels. So what we do in the display list is detect this case and say, well, this area here is completely covered by this other area, therefore we don't need to draw this one. And it reduces that layer of overdraw. So the typical case of a window background covered by a container background has now just been optimized away for you. You'll see some information about overdraw later. It's something to avoid. Basically, the more times that we need to draw every pixel on the screen, the more your application is going to suffer because the more time it takes, obviously. So by removing maybe an entire screen's full of pixels, we've removed one layer of overdraw and made things much more optimal. You should still optimize for overdraw in your application. You'll see some tools later for doing that. But in general, we try to handle this in some of the more egregious situations for you.
Yeah, actually, and so Chet mentioned, we're going to look at them, but we have tools to detect overdraw. And when you enable those tools, we disable this optimization. And that's a decision I made because I don't want you to know how we optimize your app, so you go fix your app first. Because typically overdraw means that you have too many views, so it impacts your inflation time and layout time and so on and so forth. So it's still very interesting to know where you have views that are basically useless because they're invisible. But we're still going to optimize stuff for you.
And it still costs us some amount of time to actually make this decision to see that that extra information is there that didn't need to be there. It's much better if you could solve it at the app level and that information wasn't in the display list at all. But at least we'll remove the overdraw situation when we can. So here's an example in the typical case where you have a window background. So we're going to draw the window background here. We've just had 1x overdraw. We drew basically the size of the screen or the size of the window. And then you have a container that completely covers that window. You specified some nice gradient in the back of it, completely covered the window background. Now you've overdrawn the screen twice. And then you have some views in your application which are going to increase the overdraw. The views are fine. The container background and the window background, not so fine. So you have the other situation now in 4.4 where we detect this. So when you draw the window backgrounds, well, we know when we post-process the display list that that actually didn't need to be drawn, so we don't draw it. There's no overdraw that first time. We just draw the container background and then the views that need to be drawn, reducing the overdraw pretty significantly. Bitmap reuse, I talked about this a little bit in the previous session. The necessity to do this, particularly if you're loading in large bitmaps constantly and triggering GCs in a case where you could actually just continue to use the same buffer. So in 3.0, we made a change to move bitmaps into the Dalvik heap. And it's nice if you can actually reuse the same buffer to avoid GCs so that we don't need to reclaim that memory by running a full garbage collection every time to do that. In 3.0, we introduced an API which is in Bitmap Factory Options called in-bitmap, and you can basically tell us to use the same bitmap to decode directly into that bitmap for new bitmaps that you're loading. This avoids GC because we're just loading the memory into a buffer that's already allocated. We don't need to allocate anything, therefore we don't need to collect memory in order to make space for it.
We're going to talk about that a little more tomorrow in the What's New in Android talk.
And don't we talk about it here today too?
Maybe.
Okay. All right. So we'll have some example of bitmap use later in the performance tips section that we're into now. For instance, why don't we talk about it right now? So here on the right, you'll see a video. We took this using the new screen record tool, which is awesome. So in there's different ways. So in 3.0, we introduced the new in-bitmap API, which you can see at the top. So we create this bitmap cache to be the size and the depth that we want. And then you say, I want for my in-bitmap field to use this cache bitmap that I've created. And then you set the in-sample size. There was a bug in 3.0 that was fixed in maybe ICS, I can't remember, where you had to set the sample size to 1. So in 3.0, it was very limited. You basically could load in bitmaps into the same size bitmap. And apart from that, you needed to create a new bitmap. The change in 4.4 is you can actually load in bitmaps of any size and decode into that just as a scratch buffer. So you can see some of the performance improvements here, which come directly from GC, because if you look at the log while this app was running, in one case, Does this show the checked? Yeah, when do we check that? So when it's unchecked, we're not using the scratch bitmap. We're just decoding and allocating on the fly, which means we need to deallocate the old bitmap to make space for it. And in the log, you could just see the spew of GC messages, which is directly impacting the frame rate that you see, and we're basically getting 20 to 30 frames per second. If instead we create a scratch buffer and we decode directly into the scratch buffer, you see no GCs in the log, and more importantly, you see a frame rate up around 50 instead.
So wait, what section are you in?
I think I'm in the correct section, aren't I?
Oh yeah, we reordered the talk. Sorry about that. Sorry. So I mentioned the asset atlas that we use on your behalf in the framework, but you can also use this technique in your application to help reordering and merging of draw calls. So it won't matter much in a lot of cases, but if you are going to draw a lot of bitmaps in your application, especially small bitmaps, you might want to use your own atlas. A great example would be if you have to draw a lot of emojis, those funky little smiley faces that we now have available in the IME. This is a great case for that. So there will be several performance implications. So if you use an atlas, it's gonna reduce the number of GL draw calls, gonna reduce the number of GPU state changes, and we can do better merging. So the way you can do it, I will show you some code, and I wrote this little app, so it's just drawing a bunch of photos, so it's drawing columns of photos, and it's using a sample set of 10 images, and this is what the atlas looks like. So it's a single image that contains the 10 photos, and we want to draw those photos, but instead of just copying this image on screen, we're gonna take each photo individually and draw them in columns. So first, we need a definition for our atlas. So a very good way to do this is just to create. You can do it in many different ways, but I just created a text file that I put in the raw folder in my resources, and my format is very simple. So you have the atlas name, and it's going to be the name of the drawable that contains all the images, and then on each line, I just have a name for each photo and the coordinates of the image inside the atlas. Again, there are many ways of doing this. There's no right way or wrong way. Just do whatever is easier for you. So this is the example. This is the actual set of data that I was using. So the drawable is called atlas. So it was in res/drawable-xhtpi/atlas.png. And then you can see all the texture, the coordinates, the pixel coordinates of the various images in the big texture. I wanted to show you this line of code, so I'm simply reading the first line of the atlas text file from the resources, and then I'm using this pretty awesome method called getIdentifier on the resources API. So if you look at the second parameter, we're indicating that we want to get the ID of a drawable, and the third parameter, we're passing the package name of the app. So here I'm passing the package name of my own app, but you can also use this to load resources from a different package, from a different APK. I believe we use that technique in Launcher. And the first argument is a string that contains the name of the resource you want. So when we execute that command, we're basically asking for the resource identifier for the drawable called atlas. And then we can pass that to the bitmap factory, and we get a bitmap of the right that contains all of our photos. Then I have a very simple data structure to hold all the different entries in the atlas. So we have a name that I'm not using, and a source rectangle. So we're going to store the coordinates of every individual entry in the atlas. So then all we have to do is read the text file line by line, just find all the different parts of the entries. So I'm just splitting on the comma character and just doing a bunch of parsing of ints. So it's very simple, very easy. And once I have that, in the onDraw method, all I do is iterate over the list of entries. And I use two things. So first, a destination rectangle. So this is where you want to draw the bitmap on screen. Right here, I'm using the width and the height of the individual images, but you can also use that destination rectangle to scale the images on screen. So if you use a destination rectangle that's smaller than the source rectangle, you're going to scale down, and you can make it bigger to scale up. And then I'm using this variant of draw bitmap that takes two rectangles. So the first one is the source rectangle in the bitmap, in the atlas, and the second one is where I want to put the image on screen. And this is effectively what we're doing with the asset atlas that I showed you before, except we do it on your behalf. So it's very easy to do. It can be a great optimization in your application if you have a lot of bitmaps. Here's some tricks if you want to use that technique. Make sure that you have a 1 pixel transparent border around all the entries in the atlas. If you don't, and you scale the images or you rotate them, you're going to get a lot of artifacts, and that's because of the bilinear filtering method that we use in those situations. You should also be very careful with the maximum texture size supported by your device. An atlas can get very big rapidly. And especially for devices like a Nexus 4. So Nexus 4 is a 1080p display, so your images will be pretty large. And on a lot of devices out there, the maximum dimension for an image when it lands on the GPU is 2048 pixels. And on some devices, newer devices like the Nexus 5, it's going to be 4096 pixels. And the next bump will probably be 16K. So once it's at 16K, you probably won't have to worry too much about it. You can get the maximum bitmap size from the Canvas API. There's a max bitmap width and a max bitmap height methods that you can call to get an idea of what's the maximum size. This is just a blow-up of the atlas, and you can see between the different entries that there's this 1 pixel transparent border that guarantees that we're going to get proper bilinear filtering when we do scaling and rotations. So if you're never going to do scaling and rotation and you know that for sure, you don't need that extra border, and it's going to actually save you a lot of space, but just in case, you can leave it there. Also, using an atlas will probably, especially with the transparent border, will disable an optimization. So what we do on Android is when you give us a bitmap, we look at whether the bitmap is opaque or not. And if it's opaque, we can draw it without blending on, and that's much more efficient for the GPU or even in software to do that. The problem with the atlas is because you want to have that, most of the time you want to have that transparent border, the image, as far as the framework is concerned, the atlas is not opaque, it's a transparent image. So if you know that your entries are opaque, you should tell us that they are. And the best way to do that is when you draw the bitmap on screen, you can use a paint and a special blend mode called source, SRC. And the source mode basically means that you don't want blending. So the best way to deal with this is simply to store that information in the atlas file. You can just add a flag at the end that says whether the entry is opaque or not. And that's exactly what we do with the asset atlas at the framework level. So when we store opaque bitmaps in the asset atlas, we draw them as opaque and we disable blending even though the texture in which they are is not opaque. So we mentioned I mentioned the new optimizations, the new optimization for layouts in Android 4.4, and I wanted to go into more details about multipass layouts and why they're bad for your application. I mean, you've seen that example. It was a pretty simple view hierarchy, but the number of measure calls can quickly escalate, and those multipass layouts can become very, very, very expensive. So again, there are two layouts in the framework that can cause multiple measure passes. The first one is linear layout. So for any child that has a weight, that child will be measured twice. And if you have a relative layout, every child of the relative layout will be measured twice. So relative layout in particular can be really, really bad. And you can imagine that when you put one of those things, a relative layout, at the top of your view hierarchy, it's going to cause all the children to be measured twice. And if those children causes their own children to be measured twice, then the leaves are being measured 4 times. So it's an exponential issue, and you should really avoid it. So for linear layouts, you can actually work around that. If you have a vertical linear layout, you can simply set the height of the items that have a weight to 0. So if you set the height of those items to 0, we're going to take a special path, and we're not going to measure them twice. We're going to measure them only once. And the same applies to horizontal linear layouts. There's the added trick that you need to set the baseline aligned attribute to false. And actually, the ADT, the lint tool in ADT will tell you about this, and you should really listen. The only thing is that you can't always apply those tips. Sometimes there are good reasons for not using a width or height of 0, and sometimes you actually do want the baseline alignment. So don't blindly apply those tips. Like, make sure they do what you want in your UI. But they're definitely going to help your performance. And that's my tip for relative layout.
So it's kind of an important tip because it's really easy to fall into this trap. The tools actually use ADT uses relative layout by default. I think that's because it integrates better with the visual design tool. So drag and drop, and it uses constraints, and so you can get sort of a nice visual thing just by dragging and dropping onto the UI. And relative layout worked really well with that. And that's great for simple applications, but once your application gets a little bit more mature, maybe you should not use the default that's
So I
provided.
exaggerate a little bit. You can use relative layout, of course, but be very careful. So the problem is, a few years ago, I wrote a blog explaining that there are situations where relative layout might be better than nested linear layouts, and it turned into always use relative layout everywhere for everything. Don't do that. And that doesn't mean you should never use relative layout. Try to understand the trade-offs that you're making. Make sure to profile your applications. If scrolling is slow in your application, or startup time is bad, or when you change something in the layout, it takes time for the changes to apply. Use the profilers. Like, try to understand what's going on, and knowing that relative layout can be the source of performance issues. Try to figure out whether you need them, and more importantly, make sure that your relative layouts are as far down the tree as possible, because the higher you put them, the worse it's going to get for performance.
So there's performance implications due to non-rectangular clipping because of sort of low-level details in the rendering pipeline. In particular, whether we have to apply a clip on a rectangular object or not can take us into a fast or a slow path. So in this case, we take a look at some simple drawing code. We're going to clip the rect, then we're going to rotate the canvas, then we're going to draw the bitmap. And what that looks like visually is something like this. So we're going to apply the clip to the area, then we're going to rotate that area, we're going to position the object, and what it looks like on screen is this. And you can see that the rectangle that we're clipping to is aligned with the screen. That means that we can use the scissor operation to basically chop that rectangle and say, okay, I only want to draw in this area very fast.
Just a quick piece of information. When graphics people talk about rectangles, they talk about screen-aligned rectangle, or rotated rectangle is not a rectangle to us.
And you're going to create one of those non-aligned rectangles by doing this. You're going to rotate first, then you're going to clip, then you're going to draw the bitmap, and what it's going to look like is this. We're going to rotate, we're going to apply the clip like that, we're going to draw our bitmap, and then on the screen it's going to look exactly the same. But behind the scenes, what you made us do is use a stencil buffer. Instead of that scissor, which is a really quick operation in OpenGL, we had to create a stencil buffer and use a stencil buffer to basically mask out the area that we wanted to actually draw into. Much more expensive. So don't make us do that. Another tip is to avoid updating layers. We've seen this on some applications recently, some internal applications as well, where using a layer is a good approach in general to avoid the overhead of a lot of drawing operations during an animation. So let's say you want to move a complex view or container, across the screen, or you want to fade it out. Well, maybe you could just set that into a hardware layer and then run the animation on that property, which means that every time we redraw that in the new position or with the new alpha value, we're not actually issuing GL calls. Instead, what we're doing is we draw it once into a texture, and then we just copy the texture around, which is super fast in GL. Right? So good idea in general. However, if you create a layer out of that object, and then you go ahead and change the object while it's layered, like let's say one of the views inside of it has its text changed, or there's a color update, or the container itself changes. If anything modifies that view or the container or the hierarchy inside it at all, that means we need to redraw into the layer, and that is an expensive operation. So use a layer when you can, but avoid using layers if you actually need to change the view, or more particularly, avoid changing the view while it's inside a layer. So these are just a couple of different ways you can actually set a layer. One of them is explicitly you can set the layer type on the view. You do a bunch of stuff like set up the animation, run the animation. When the animation is over, then you unset the layer by setting it to layer type none. Or it does it implicitly if you use the view property animator API. When you run an animation in there and call with layer, then we create the layer, we run the animation, then we destroy the layer at the end. Let's talk about some tools that we have. So we talked about non-rectangular clipping before and when you want to avoid it. And there's a tool that's in the platform now that you can use to detect when it's actually in use. So you can see in this example that just went away. So you can see these blue areas, these artifact areas here. Yeah, there you go. All right. So see the blue text as it rotates? You'll see that there's no blue background when it's actually in its default position, just horizontal position. That's because we're actually using the scissor to clip the rectangular area. Similarly, with G+, you can see as we're scrolling the stream here, some of the areas are purple. Those are being drawn with this blue highlight color to show that we've got these non-rectangular areas. The cards, as they come into the stream, are being tilted, and we're having to clip them to a non-rectangular area. We can do it. This is why we implemented it, so that we can actually do the functionality that you want. But if you detect that we're actually doing this in cases where you don't think it should be taking place or where it is a performance issue for you, then this tool gives you a way to detect that.
And G+ should probably not be doing that.
We'll have a chat with the G+ folks when we get back.
Yeah, go ahead.
So
another example in
yeah,
G+.
So the other thing that I was talking about a couple minutes ago was updating the layers. So G+ did the right thing by creating these layers because they were going to just move them on the screen. It was going to be simple transformations, and that's something that we can do very efficiently with layers rather than redrawing all the elements inside these containers. However, they're doing something to actually cause us to recreate the layers at the same time. So yeah, that was great to use a layer, but it was not great to tell us to recreate it along the fly. We're spending far too much time redrawing the contents inside a layer, recreating the layer, and then drawing the layer.
So what's actually pretty awesome about G+ that scrolling the stream is now pretty smooth on the Nexus 4, for instance. And when you see that they do two of the worst things you could be doing for performance, it makes me pretty happy about the state of the rendering pipeline. Because if they manage to get rid of the layer updates and the non-rectangular clipping, then the scrolling will probably be really, really nice. So overdraw debug, so we talked about overdraw automatic removal before, and those are the two tools you can use. How many of you have used the overdraw debugging tools before? Okay, just very few people. I wrote about a year ago a very long article explaining how to use that tool and what to do using an existing application. So just look that up. It's very useful. But this is what it looks like. So we have two different debugging tools. There's one that was added in Android 4.2, the one on the left, and the second one was added in Android 4.4. So the one on the right, so in Android 4.4, gives you an overdraw counter in every window. So here, for instance, you can see that the settings application has an overdraw of 1.29x, which is very good. So typically you want your app to be below 2 if that's possible, but if you're at 2, 2.5, that's good. And the color of the counter will change and get really red when you're doing something bad. If it gets above 2.5x, you should really try to optimize your application. So this is just a very simple indicator. The tool on the left will actually colorize the different areas of the screen that you are painting several times. So the areas of the screen that use normal colors have been drawn once. The areas in blue have been drawn twice. The areas in green have been drawn 3 times. And areas in red, it's a little hard to see, but if you look at the text, the off-on toggles, the text is in red. That means that those areas have been drawn 3 times or more. So typically you would want to see only blue or green. And let me show you what that tool looks like in action in an actual application. So I turned on the overdraw areas, and we're going into the Play Store. And it can be a little difficult to understand the overdraw when it's an application you're not familiar with. But for your own application, you'll understand, like, what is blue when it shouldn't be, what is green when it shouldn't be. So you can see here, there's a very interesting actually case right there. If I can, okay. Let's try that again. No, this one. Okay. If you look at the ratings in the Play Store, so the little stars, you'll see that they are all red. And it seems to be because there are 2 types of stars. There's the empty stars and the full stars. And it seems that to draw the full stars, we first draw empty stars behind them. So we do a lot more work than we should be doing, and it's probably a bug in the framework. So another very useful tool that was added in 4-point-something, 4.2 or 4.3, I don't remember. It's an on-screen profiler. So you can turn that on from the developer settings, and it's going to show you the time it took for the last 128 frames to draw. And every column is 1 frame. And you can see four different colors. So the blue at the bottom is how much time it took to execute your draw methods. So in the Dalvik runtime,
including our draw methods,
yeah.
either the draw methods that draw a button or draw your custom view. All the canvas
so
drawing
if you see a
operations.
lot of blue, then that means you're doing something bad in the draw methods, or we're doing something really bad. The red is the time it took for the OpenGL pipeline to transform the canvas drawing commands into OpenGL commands. So here it's really fast. So if you see a lot of red, it could be a bug in the framework, but more typically it's because you're sending so many drawing commands that we're just overloading the GPU with drawing calls. The orange is not terribly meaningful to you guys. It's basically the time it takes to send the commands to the GPU. Sometimes it will be high, but there's not much you can do about it, so don't worry too much about it. There is a green line as well. The green line is the 16 millisecond threshold. So every time you cross that line, that means you're not running at 60 frames per second. So this is a great way, you just turn that feature on, you just use your application, and every time you cross the line, you can see what you are doing, and you can try to pinpoint that in your code and figure out what was happening. There's a type of jank that we see a lot that will not be shown by this graph. So if you block the UI thread between frames by doing a layout, by doing I/O operations, by whatever you're doing, or just slipping a thread, this is not going to show up in this tool. You have to use a different tool for that. So if you see that the graph, that everything is under 16 milliseconds, but your scrolling is still choppy or your animations are not smooth, then you have to use a different tool for that.
The tool has actually been there for longer than the graphs on the screen. There's a command line tool called gfxinfo. So if you're on an ADB shell, dump sys gfxinfo, I think as far back as Jelly Bean, that would spit out exactly this information. But in the next release, then it became an option to actually put the information on screen while you're running it, so it's a little easier to equate what's happening on the screen with what you saw for performance. Procstats. We talked about this briefly in the previous session on memory. This is a tool introduced to help us optimize memory for processes, see what's going on, and hopefully help you as well. I'll walk through it quickly because maybe most people were here a few minutes ago. There's a bar at the top. The red, yellow, green one indicates how much time during the sample period it spent in critical, moderate, or normal situations. And then the bars at the bottom, the percentage indicates how long these processes have been running for that sample period. If you're running 100% during a long sample period, that's probably a bad thing, and you should find out why your activity, even though it was sitting in the background, was actually being run actively the entire time. And the blue bar indicates the relative weight of the memory that it's taking up. The larger the blue bar, the larger the memory footprint of the process. You can click on each one of those and get the screen on the right, which tells you more information about how much memory the process was consuming, as well as what things were actually keeping it awake, like what other background services were calling into it and requiring it to be awake in that time. And you can get the same information and more from the meminfo command. And you can get more information about these things in general in there's a memory document on the developer site for Android. GL Tracer is an interesting tool if you do graphic stuff. Actually, has anybody heard of this tool before? Anybody use this?
You might want to. Why don't we launch it to show what it looks like? We have time.
Do we?
Yeah.
Okay.
I think you have a trace. I got you confused. Come on.
I'm going to have to use my...
So the GL Tracer tool is mostly useful if you write OpenGL code, but it can also be useful to identify performance issues if you have custom drawing code or if you have overdraw issues, because you can use it to record all the drawing commands that happen in your app, and you can replay them one by one and see exactly what is being drawn when.
Entertain them with a song. I have to find the perspective for GL
You don't want me to
Tracer.
sing.
GL
Yeah, so the tracer for OpenGL is hidden in Eclipse, so you have to open the perspective for it. You can also find it in a tool called Monitor that's in the SDK. So if you use Android Studio, you will have first to launch the Monitor application, then you can launch tracer for OpenGL. You can use it for two different things. You can use it to replay recordings of previous sessions, or you can record your own sessions. And so this is what it looks like. Let's make it full screen. So Yeah, in advance. Usually you don't want to look at the first frame because the first frame will do a lot of setup for OpenGL and it's going to contain a lot of things that you don't care about. And you can see in the bottom right, you can see a summary of the frame, so you're going to see what that frame looks like. So you can actually use that tool to record animations and replay them. There's an artifact in that frame. We had a bug. Don't worry too much about it. And if you look at the Details tab that Chet just made very small, you can see the state of the screen for every drawing command. So the drawing commands on the left side are highlighted in blue, and every time you click on one of them, we update the Detail tab, and you can see exactly what we're drawing at that point and when. So that will give you an idea of how good we are at reordering and merging, and you can maybe try to optimize your application to make the merging perform better. And again, you can also see, like, if you have clipping issues, if things are not drawing in the right place, you can use this tool to replay the frame and see exactly what's happening.
If you really want to know the gnarly details too, you can poke around the GL state and see things like what was the shader loaded during this drawing command. You can also have it retain textures and see the state of the textures at any given time, which is really helpful for debugging things like text rendering with the glyph cache. So very useful tool if you need low-level graphics detail. Back to slides. Systrace. So very useful tool. Who's used Systrace? Not many people. Okay, so it's a little daunting at first. We're going to run through a couple of case studies here and see what the information is. There's a lot of information in there, and not all of it is obvious still to me. But there's key pieces of information which you really can't get from any other tool. When we were working on Jelly Bean, I think it was for the butter stuff, make the system smoother, we had this overall problem with the history of Android where sometimes your activity would pause, it would hiccup, what we called jank. And we didn't know why. The activity itself was fine. If you ran trace view on it or other profiling tools, things looked fine. There wasn't GC happening. What was going on? Wouldn't it be nice to know what was going on somewhere else in the system so that you could actually track down the source of this problem? So that's why Systrace was written. It we've instrumented the code at the native and the Dalvik level to put these tags in the stream so that we know what happened when. It's kind of, it's not sampling, it's a tracing profiler, but only for specific tags that we've plumbed in the code. And then we output when those things happen into a stream, and then we process that into an HTML file you can load and get a visualization of what was happening when, and then what else was happening in the system.
So Systrace is not a method profiler, so it won't show you everything that's happening in your code, but it's not a sampling profiler either, so it's very accurate. And there's almost no overhead. So you can run Systrace to profile animations, for instance, and that won't affect the performance of the animation. So it's not intrusive. It's going to get you a lot of data, but you might have to sprinkle your code with special API calls to figure out what's going on. And this is the API that was added in 4 point something, 3, I think. And it lets you create your own blocks of instrumentation, and you'll see in Systrace what it looks like. But basically, you do a begin section, end section, and everything in between will be measured in Systrace. Yeah, we'll go back to Systrace. Just wanted to show you real quick. So we talked about ADB shell dump sys meminfo earlier. So in Android Studio, if you go to the Android DDMS tab at the bottom, it's tab number 6. There's a little icon, the third icon from the top. When you click on it, you get this little pop-up, and and those are basically dump sys commands. So if you click memory usage, you're going to get the result of ADB shell dump sys meminfo for your process. There's a lot of really useful information in there. Even if you don't have issues in your application, you should go click on every one of those items just to see what kind of data you can get out of the system, because one day for debugging, it might be very useful to you. So familiarize yourself with that information. I mean, we spend countless hours in those dumps for performance tracking, memory leaks checking, that kind of stuff. So speaking of Systrace.
Okay, so here's a little snippet of information sort of typical to Systrace. You see this tree of things, the methods that it was in which are, in Systrace, it's the tags that it was within. So you can just see a little bit of information there, but let's actually take a look at a couple of runs and see what's going on. So first of all, let me see. Yeah, there's videos here. Okay, so first of all, we'll look at this case. There's a particular animation case that I wanted to demonstrate, show people how to do, where you're launching from one activity into another. It turns out to be tricky to just use the standard window animations to do really custom things. You can scale, you can fade, you can move, but you can't really move the contents in the exiting or the entering application. For that, you really need custom animations that are actually running within the activities themselves. So the technique for doing this is to launch the new activity in a transparent window and then animate the stuff in the old activity and the new activity and make it look to the user as if it's sort of one blended application. It's a nice look. There's some details about how to make that work, which we'll probably talk about in our talk in a couple of days. But in this particular case, what I wanted to do was animate out the things from the exiting application, and then while that was happening, in the middle of that animation, I wanted to then launch the new activity and go into that and animate some information into that new activity. So we can see here at the beginning of the video, we've got a bunch of grayscale thumbnails. They're animating out of the way, and then one thumbnail is retained, and then that animates and colorizes and zooms up into place. That's the second activity. So the first activity has a bunch of thumbnails. We click on one of those, it launches the second activity, and it animates that one thumbnail up into view. Now the problem with this, if we get out of the presentation stuff and go into the actual videos, I call it activity transjank, because, so I'll step through right there. Okay, so I'm using QuickTime, I'm just frame stepping here.
So the new screen record command that in Android 4.4 that you can use to record videos like this is also a useful debugging tool, because if you have performance issues in your scrolling or animations, you can just record the screen and then play it back frame by frame to see exactly where the prime occurs.
So I'm going to click frame by frame, and then at some point you'll start seeing some pauses. Frame, 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 frame. So we just skipped a frame. Then we hop a little bit because we skipped some time has passed, so we hop further. Then we skip another frame. Then we skip another frame. So we're missing like 2 to 3 frames for a few frames, and then we go back to normal animation. So wouldn't it be nice to figure out what was actually happening there? Why did we have that janky experience? It wasn't too bad, but it was noticeable to the user. Things were moving smoothly, and then they hopped and skipped a couple of times. So it would be really nice to figure out what was going on in the system. So we have that's, let's see, trace activity transjank. So this is a systrace that I took at the same time as I was doing the screen record. So if we take a look at the output here, bunch of information. You have options on what you can ask Systrace to record. So I was asking for SCED information, for Dalvik, for graphics, for views, sort of typical stuff that we like to see and look at in parallel to what else is going on in the system. And here's the information for the process that I care about, this activity anim down here. So if we zoom in here, you can see we're running a bunch of animations there. These are all the thumbnails that are being animated out. And then while those are animating, we can see this is the normal drawing process. For any frame, what you're looking for is this call to perform traversals. That's where we do measure, layout, draw. Every frame, measure, layout, draw. Some of those don't need to happen. Maybe measurement didn't need to take place, layout didn't need to take place, and it's all about drawing, which is the case here. So all of this stuff is happening normally. If I zoom out, we've got, these blocks that are from just a couple of milliseconds, 7 milliseconds up to 16. Okay, so some of them are crossing a frame boundary. Not great, but it's doable. But then we come over here, and all of a sudden we have a break in the flow. So what's going on? So we've got, normal rendering, normal rendering, normal rendering, inflation. So what's happened was we've launched the second activity, and it's being inflated. And this is the point where you have an aha, because you think, well, it's a separate activity. Why is the inflation happening in the middle of my, drawing process for my main activity? Because it's the same process. Right? We always have one single UI thread for any given process. The activity manager makes sure that everybody gets the same UI thread. If you're managing resources between different activities in your process, they can do that without running into concurrency problems because they're all in the same UI thread. So it's good in general for multi-threaded programming because you just have this, one thread that you have to deal with. However, this is where the problem hits because I say, okay, main activity, I'm halfway through my animation, launch the sub-activity, and sub-activity says, great, let me load myself. And we freeze on the UI thread because that's where inflation happens. And then we lay out, so we have a long rendering process for that other activity to actually figure out where it wants to draw stuff on the screen.
And there's also a GC.
Oh, and there is a GC there. That's nice,
Can you zoom in on it?
What's that?
Can you zoom in on it? So here you can see during inflation, we're inflating a class called shadow layout. Might be hard to read for you, for the people in the back. And inflating that class took 32 milliseconds, but most of that time was spent doing a garbage collection. And that's why, in the first part of this talk, we kept talking about, trying to not create temporary garbage and be very careful about reusing memory, because when the GC triggers, you're going to block for 25 milliseconds, and 25 milliseconds is going to make you skip a couple of frames, and your animation is going to suffer as a result. So we have two types of GC events on Android. There's one called the GC for alloc. That's the one that you're seeing here. So the GC for alloc is the worst kind because it's going to block everything. And the GC for alloc will happen if we are really running out of heap and we need to run the GC to make sure your allocation succeeds. So most likely what was happening here, the shadow layout was probably allocating a bitmap to create the animation. And to be able to allocate that bitmap, we had to grow the heap and collect a bunch of garbage. The second type of GC is called the concurrent GC. That one will only pause the threads for a little bit at the beginning and at the end. And the rest of the GC will be concurrent. So even the concurrent GC will pause threads for maybe 3 to 4 milliseconds at the beginning and 3 to 4 milliseconds at the end. That's a lot better than the GC for alloc. But you're going to lose, 6 to 10 milliseconds to a concurrent GC, and that might be enough to make you skip a frame.
Once the second activity was up, it had a more expensive time sort of doing the measurement and layout that it needed to do to figure out when to draw. And then we can see animations got more in sync. And you can also see here more of the dynamics of the single UI thread, because in any rendering pass now we do perform traversals on one activity and on the sub-activity. They're both in the same UI thread, so all of it has to happen in the same thread. So the longer you take in any one of those activities, the longer you're going to take for both of them to happen to maintain a reasonable frame rate. You're going to have to work at that. So the takeaway here was, it was kind of the aha of, oh yeah, that's right, we're in this single-threaded scenario, and maybe the experience that I was trying to get from that particular animation isn't going to work as well as I wanted it to, because there's really no way around that. Inflation happens on UI thread. First layout and rendering is expensive, and if I'm going to do that in the middle of an animation that the user is looking at, maybe that's not going to be a good experience. What I would probably do in this situation instead is either skip the animation on the exiting application entirely, or finish that animation, so let the thumbnails actually animate all the way out, and then right at the very end of it, then launch the second activity. And we're already done with the animation anyway, so the user is not going to notice a jank as the things are moving along and then suddenly hiccuping.
And a great way with Systrace to see whether you're skipping frames, when you zoom out, now that you've noticed that we have those patterns of green for perform traversal and purple for the draw, and that's always the same color. So every time you record the Systrace, you will see the same colors. So when you zoom out, you can see the patterns of frames. So you can see the animation, we see a lot of frames. So every time you see a gap, and they're pretty obvious, we can see like there's a big gap, then you know that there's a prime in the animation. Of course, we only draw on demand, so if there's nothing to draw, we'll stop drawing. But most of the time, if you record the Systrace during animation, and that's why we introduce those new animation tags, you will know that you skipped a frame during draw. Before we go, do you want to say more about this one?
No, go ahead.
Okay. I wanted to tell you a little bit more about Systrace, because there's a lot of very useful information. So if we zoom in all the way here, you can see right above, so this is our main thread in our process, and right above the tags, you can see this little colored line that gives you the state of the thread. So when it's green, it means you're running. When it's blue, it means you're runnable, which means you're not being scheduled on the CPUs. And when it's white right here, it means that you're sleeping. So what's very interesting here is you can see all those white gaps in a bunch of places. So that white gap here means that we are waiting for something else in the system. We are waiting on a thread. And if I zoom in all the way here, I'm going to see that little blue thing. And if I, let's see, where is my, you're missing information. I'm going to show you that in a different trace. But you can use Systrace to figure out what thread you are waiting on and understand why we were pausing at that point. Based on the other tags, it seems we were starting a new window and we're just waiting for the window compositor to give us a buffer, which takes a bit of time. Again, you can create your own tags to add information in there. It's very useful. You can also go all the way back up, and if you have the right options enabled, we can zoom in on the CPUs. So here we had 2 CPUs online. So even if you have a quad-core device, you might not see 4 CPUs. You're only going to see the CPUs that were busy while the trace was being recorded. So if I zoom in on it, I can see exactly what was going on. So I could see, for instance, here that our application was scheduled on CPU number 1, while the CPU number 0 was running compiler. So compiler is probably the shader compiler or the JIT. We can see the service manager running. We can see our application running again. So it's a very useful tool to understand what's going on in the system. And you might be surprised by sometimes in your applications, some of the API calls you're going to make, like querying a cursor, they will make you do an IPC. So you're going to cross process boundaries, and your performance issue might come from the fact that you're calling into another process, and that other process is busy because that other process is doing a GC. And Systrace will show you all that. And actually, before we look at the second trace, could we launch monitor? Just wanted to show how to. I want to show you how to launch Systrace real quick. You can do it from the command line, but in the latest version of the SDK, it works really well from monitor itself. Just go to DDMS. That's fine. Yeah, or you can do it from ADT in Eclipse. Just go to the DDMS perspective.
Tab, which is not here. That's why I was changing perspectives.
Okay, sorry.
All right.
You're an Android programmer without DDMS, whatever. We actually use our tools from the command line most of the time, or we use the standalone version of the tools. So if you want to run Systrace, you do not have to select your process, because Systrace is a system-wide tool. So here, this little icon that looks like, I don't know.
Cupcake. Looks like a cupcake with androids on top.
Looks like a cupcake I would not eat. So you can click that little button. You can choose the destination file for the trace. So Systrace files are HTML files. They're completely standalone. You have to open them in Chrome. But the nice benefit of that is you can just send them by email. You can attach them to bug reports, and anybody can open them. You can specify if you want the trace duration. By default, it's going to be 5 seconds. The trace buffer size, most of the time you won't need to change that. It's only if you have a lot of tags. You might run out of buffer. And here you can specify what tags you want to trace. Most of the time, when you're just looking at performance issues in UI, the tags you want are graphics, view system, the CPU frequency, the CPU scheduling, and Dalvik VM. So graphics will show you when we're drawing. A view system will show you things like layout, inflation, measurement. Dalvik VM will show you all the garbage collection pauses. So if you don't specify the Dalvik VM, you might see weird gaps in your app and you don't know what's happening. Very often it's going to be a GC. The CPU scheduling is what I was just showing you. It will show you what process is running on what CPU. Sometimes performance issues can just be a prime of scheduling on the CPUs. And the CPU frequency is also interesting because we've seen problems in the past where the app was being slow. But the app itself was fine. It's just that the CPU was running at the lowest speed. So the app was not doing enough work to be able to raise the frequency of the CPU. So the app was too optimized. So the kernel was lowering the frequency of the CPU, and therefore we were running too slow. That was the first time I think I wrote code that was too efficient.
And there's also the app tag. The API that I showed before for enabling traces. If you put traces in your own app, then you need to tell us about that application so that we'll inline those with the rest of the information.
Yeah. And this is an engineering device, so there's a lot more showing up than it will for you. Anyway, so that's how you run Systrace. And now, do you have the video for the recent jank?
Yes.
So now we're going to show an example of a jank that exists today on the Android platform and that somebody noticed on Twitter, I think it was. Somebody was mad at you, or G+. Somebody was mad at Chet because he saw a frame of jank, and we wanted to look at it. So this is what, Nexus 4?
Nexus 4.
Nexus 4. So if you look at the recent button in the bottom right, you can see that when we press it to go into recents, there's a little jank. The highlight, yeah, look at the highlight animation on the recents button.
Frame. See it pause there for like frame. We skip about 4 frames there on that fading animation. And you're saying, eh, and we're saying, ugh. So then we have
let's open the trace.
a systrace for that, which is trace recents.
All right. So I don't remember what the problem was, so I'll try to figure it out again. So that trace is a little different from the previous one because the previous one did not have the CPU frequency tracing, and that's those green bars here. So it's a histogram. So when you click on it, you can see the value of the histogram at that point. So for instance, here at the beginning, the CPU on the Nexus 4 was running at 384 megahertz. Then at some point, we started an animation. We went all the way to 1.5 gigahertz. And then, you know, as the workload is down, we went back down to 100 gigahertz. So again, that can be very interesting to see, to make sure that the CPU is doing what it's supposed to be doing. And you can see that we have 4 CPUs online. One of them, CPU number 3, didn't do much work, but CPU 0 and CPU 1 were very busy for that time. Anyway, so you can collapse. There's other interesting stuff. So all those things right here with names that I don't understand, they give you the frequency of various buses on the phone. Those will be different from device to device. But here, for instance, we can see the frequency of the GPU instead of the CPU. But we're not interested. Let's see, where's our process? That's launcher, system UI, is that the one? Yes. So here, again, we can use that pattern that I was telling you about to figure out when there's a jank, and you can see one here. So there's this big block of perform traversal, and there's no frames, even though we are running an animation. So if I zoom in on it, we can see that the thread was sleeping, and we were waiting on something. And I have to go at the end. Let's see. Sorry. If we go at the end, there's a tiny blue bar. So we got a wake up from thread number 19652. So instead of remembering the thread name or the thread number, you can use the timeline at the top to create guides. So here, oops, where am I? What did I do? Okay, so it's at the right place. So what I want to do is, I was woken up by a different thread, so I want to figure out what that thread is. So I just create a guide, and then I'll go all the way back up to the CPUs and see what was running on the CPUs at that time. So if we go all the way back down, here we can see something called the binder C, and that binder C happens to be the thread that we are waiting on. So then we can try to figure out what that binder was. So binder threads are what we use for IPCs. And where is it?
Something.
Don't we have that information? No, that's recents.
You're saying a typical Systrace debugging session.
Yes.
Wow, there's a lot of information here. How do we understand this?
Binder C, I have no idea what it was doing.
Binders can be used.
Yeah, here it is.
Yeah.
It's in this process 15922.
Screenshot client, yay.
So basically, we were waiting for the window manager to give us a thumbnail for the current application. So it seems that what's happening is when we're on the launcher, we bring up recents, and launcher the window manager is taking a screenshot of launcher that we never show in the recents. So it sounds like a bug on our side. We shouldn't be doing that because we are blocked waiting for that screenshot.
In fact, there was a related bug fix just recently where we were, related to my activity transition example, where we were screenshotting a main activity when going into a sub-activity. We don't care about the main activity. We're still in the same process, so there was no reason to take a screenshot. So that saved us, 100 milliseconds by not bothering there. It looks like maybe there's other places in the platform where we have that same issue.
And of course, this is just a quick example. Like, we can't, unfortunately, tell you how to use Systrace because it's going to depend on what you're doing, and it takes experience to understand how to use it well. But if you do a lot of multi-threading in your applications, Systrace is a wonderful tool because you're going to see all the threads running at the same time. And you're going to be able to identify possible performance issues related to the interaction between your threads. For instance, we saw that with a coworker. We were looking at the Play Store, and there was a little hiccup. And turns out that it seems that it was caused by the priority inversion between threads in the Play Store process. So one of the background threads had a high priority that it shouldn't have had. Anyway, so there's a lot to do with Systrace. If you've never used it, you should really go take a look at it. As you've seen from Monitor or Edit, it's really easy to launch. And it's going to give you a lot of insight on what's going on in the system and in your application.
There were sessions at Google I/O this year as well as last year that had smaller case studies about using Systrace in different situations. It's worth checking that. And is there a doc on the developer site?
Yes, on developer.android.com. I think it's in the training section. There is a document that explains how to run Systrace and gives you a little bit of information how to use it and what it means, what's on screen.
Oh, I wanted to mention too, I added app tags to the app, and I think I produced a different trace file that we didn't load in, because I wanted to show how it's really helpful to sort of block off a section where you say, well, this is where I was launching the activity, from here to there, what was going on at that time, and then to see the other trace tags as part of that envelope to sort of see the nesting of logic there was very helpful.
I want to show one last thing with Systrace that's actually pretty cool. You can create a selection, so you can select a bunch of, a part of the timeline. And here at the bottom, you will see the total time spent in every tag, but you can also see the number of occurrences. This is actually, so earlier I showed you the number of calls to onMeasure. That's how I looked at the number of calls to onMeasure. So I just added a tag in my application, and then I go in Systrace, and I just select the timeline, and I look at the number of occurrences of that tag, and it tells me how many times we've executed that piece of code. Anyway, so, and that's sometimes a good way to just figure out, like, at the high level, you want to select everything, and if you see that you're doing view stub and frame layout, that means we're inflating something somewhere. So then you can try to zoom in and dig deeper.
And that's it. That was the performance talk.
So if you want more information, you can follow us, actually mostly Chet, I'm sure now that I don't work on Android anymore. So on G+, on Twitter, check out our Google I/O talks. We have a bunch of talks on parlys.com from previous years at DevOps. Check out the Dev Bytes on YouTube. There's a lot of great information there. We also have a lot of really interesting articles in the training section of the developer.android.com website.
And more stuff coming out all the time. There's a bunch of stuff on KitKat that just came out a couple of weeks ago.
And it's highly unusual, but we have time for questions, so ask away.
Thank you.
So that guy didn't want questions. Yes? So you've created enums. I can barely hear you, sorry.
I ignored your advice and I created some
Okay.
enums. Can you talk to me about using enum sets? How's my memory use there?
Yeah, so the question is, if you have a bunch of enums and use enum sets, what's the memory usage? I do not know. I would have to look at the implementation of enum sets. I don't know. The biggest issue with enums for us is mostly the code bloat, not necessarily the memory usage. Although, of course, all these instances might be an issue. So based on the information we gave, you can go look at the implementation of enum set and try to figure out, like, roughly what's the memory usage. And again, measure your app and see if you have memory issues first. See if it's a problem.
Right, and it's probably easy to misunderstand what we were saying before. We're not saying that that's a mistake that you used enums. We're saying be aware that enums cost in terms of memory performance, so that if you have issues, just be aware of the trade-offs when you're writing the code and designing the architecture. Another question anywhere?
I think they're
Nobody.
so bored they want to leave.
I think they're asleep. All right, that's it. Thanks.
Thank you.